Hi everyone, my name's Nari,
And I'm Samira.
and this is your crash course to quantum mechanics.
It's everything you need to know for test number 3 in 15 minutes.
Yep, and periodic trends. Okay, so ionization energy. You need to know it for the exam, and it's actually a really easy concept to understand. You just gotta find a way for you to get it in your head, to understand it. All right, and hopefully my analogy will help you guys. So ionization energy is defined as the amount of energy required to remove an electron from a gaseous atom. You guys need to be aware of that because Rogers does have a tendency to test you on the definition of that on the exam. Think about an old lady walking down the street and she has her purse held out like this in front of her. She's walking down a pretty sketchy road. So it'll be pretty easy for someone to come and yank that purse out her hand and, rob her of her money. Whereas, what if a lady was holding her purse close to her chest like this and walking down the road? It's going to be a lot harder to steal that bag as opposed to the lady who's been holding her bag like that, right? Ionization energy is the same thing. If the electrons is closer to the nucleus like that, it's going to be a lot harder and it's going to require a lot more energy to steal those electrons, all right? Whereas if the electrons are out like that, it's going to be a lot easier to steal those electrons. So what pulls in the electrons like that? The protons. The protons pull in those electrons, all right? So the proton is pulling the electrons inward, which makes the size smaller technically. That's why you would look at the nuclear charge in order to determine which one would have the higher ionization energy. And typically, the one with the highest nuclear charge would have the higher ionization energy than as opposed to an element with a lower nuclear charge. Okay, so this is typically the type of problems you'd see on Dr. Rogers' exams, right? So you'd have either the second ionization energy compared to the second ionization energy of a certain atom, or you might even have the fifth ionization energy compared to the third ionization energy of a certain atom. It really just depends. So we've got the second ionization energy of lithium, and then we also have the second ionization energy of beryllium. And the steps Dr. Rogers advises you to do is to first always write down the electron configuration for both. And then you'd write down, and then you'd look at the nuclear charge or the amount of protons available in each atom. The electron configuration for lithium is 1s2, 2s1. And the electron configuration energy for beryllium would be 1s2, 2s2. Guys, I want you guys to note this. We're looking at the second ionization energy. That means we already took off an electron for the first ionization energy. So technically, lithium isn't in this step anymore, neither is beryllium. So lithium already removed an electron, so we might as well just look at it where we are right now, right? So we'd remove this electron right here, and we'd be in the 1s2 shell. And then beryllium would be in the 2s1 shell. So now we're looking at the 1s2 electron shell of lithium, and we're looking at the 2s1 shell of beryllium. Since they don't have the same electron configuration, we can just look at that. We don't need to really look at the protons or the nuclear charge. So lithium is in the 1s2 shell. Beryllium is in the 2s1 shell. Beryllium's shells, this is beryllium's outermost electron. This is lithium's innermost electron. That means that it's going to take a lot more energy to remove an inner core electron than it is to remove an outer valence electron. Because those valence electrons, they're not being held in as tightly as those inner core electrons. So since beryllium still has its valence electrons out in the open, it's going to require less energy than to remove lithium's inner core electrons. So that's a concept you should be aware of. The ionization energy of inner core electrons are always greater than the ionization energy of valence electrons. So, saying that, lithium would have the greater second ionization energy than beryllium. Hopefully that helped you guys. We're going to be moving on to harder problems in just a minute. Okay, so this is a different type of problem where we're comparing two different ionization energies. So we're looking at the third ionization energy of boron compared to the second ionization energy of beryllium. So the electron configuration for boron was 1s2, 2s2, 2p1, right? But we're looking at the third ionization energy. That means we already took off the first and the second, so we took off 2 electrons already. So let's go ahead and do that. So 2p1 minus 1 electron would leave us in the 2s shell, minus 1 electron would leave us in the 2s1 orbital. Alright, same thing for beryllium. Its electron configuration is 1s2, 2s2. But we're looking at the second, that means we've already taken off 1 electron. So let's go ahead and look at it like that. So right now, we're at the 1s2, 2s1 shell. We have the same electron configuration, so now that we've already looked at that, we can check that off. But now we can look at the protons or the nuclear charge in order to determine which one has the greatest ionization energy. Boron has more protons than beryllium. So since they're in the same shell, we look at the protons or the nuclear charge to determine which one would have the greatest ionization energy. And boron has more protons than beryllium. So I remember that old lady, if she's holding her purse in like that, that means it's gonna require a lot more energy. And the protons are pulling in those electrons like that. So beryllium, they're not really pulling it in that much compared to boron, where they're pulling it in like that. So since boron has more protons than beryllium, boron would have the greater ionization energy. So the third ionization energy of boron is greater than the second ionization energy of beryllium.